Okay, in this third video on C3 differentiation, we're going to have a look at differentiating log x or ln x. So we're going to start by defining y is equal to ln x, which is log to the base e. So if y is equal to ln x, then just by unwrapping it, we can say, if I just put in here that, remember, this is log e of x, we can apply this back the way, and this means that we will have e to the y is equal to x. Okay, just sort of unwrapping our log. Right, so now if I want to differentiate e to the y, I can differentiate x with respect to y, because my function is x is equal to some function of y. It's like f of y, really. So it'll be the differential of x with respect to y. Okay, so we've got dx by dy, but what we actually want is dy by dx. So dy by dx is just the reciprocal of dx by dy. This is equal to 1 over dx by dy. So this means that dy by dx, the thing that I'm actually wanting to find, will be 1 over e to the y. Now if we remember, e to the y is just equal to x. So this gives me 1 over x. So this means we have proved if y is equal to ln x, dy by dx is equal to 1 over x. And this is a very important result that we're going to be using a lot, so it needs to go into your notes as a key fact. Let's have a go at something a little bit more interesting. Now this is pretty cool. We're going to look at when y is equal to log of some function of x where k is a constant. So we're talking about 3x, 7x, something like that. We're going to have a look at differentiating this. Well, if we think about our log laws, we can just split this up using log AB as log A plus log B. We'll get log k, ln k plus ln x. Now we want to differentiate it. Well, we need to remember this guy is just a number. Whatever k is, ln 3, ln 7, ln 6, it's just a number. So when I differentiate it, it's actually just going to disappear. So when I find dy by dx, or y prime, this guy is just going to disappear, and we're going to just differentiate ln x. And when we differentiate ln x, we just get 1 over x. So we get this fabulous result that actually, if we differentiate with respect to x, ln of kx, we will literally still just get 1 over x. It doesn't make any difference, the fact that we've got a number in there. Right, now let's try some chain rule with lns. Okay, let's have a go at differentiating this composite function, ln of a function of x. So ln is one function, and then inside that function we've got this x squared minus 5, another function. So this is chain rule because it's a composite function. So the chain rule says that I'm going to take my f of x, if you like, my function, ln of something, and differentiate it. So I'm going to differentiate the ln of something. Well, ln x is 1 over x. So using my substitution, I'm just going to get 1 over x squared minus 5. That's like having ln of t, if you like, where t is equal to x squared minus 5, if we're doing the chain rule the long way. So the differential of ln t is just 1 over t, and t is just x squared minus 5. But remember, we need to times by the dt by dx, the differential of the thing inside the brackets. X squared minus 5, the minus 5 goes to nothing, and the x squared goes to 2x. So if I simplify that, I've got 2x over x squared minus 5, and my job is done. Right, if you want to practice some of these will be on exercise 5 of the Elmwood textbooks, the textbooks that you've currently got. And if you start on page 82, goes right the way through to page 84, you can have a go at practicing everything to do with ln differentiation.